I didn't talk about these yet. All right, so writing equilibrium constant expressions is the first section of homework, first group of homework problems. So based on these descriptions, write a balanced equation and the corresponding Kc. And so here, it's just nomenclature, carbonyl fluoride. This is a triatomic, not triatomic, but a ternary compound. There's more than two elements. Decomposes into gaseous carbon dioxide and gaseous carbon tetrafluoride. So we come up with a balanced chemical equation, then we write the Kc expression. Kc would just be products over reactants, raised to the respective coefficients. And so we have three of those. So those should be pretty straightforward. Here, we want the Kp instead of the Kc. So we could do that. Number 2, chapter 15. These are a little easier because they give you the balanced chemical equation here. So they're asking for Kc, so it'd be NO2's concentration squared divided by the NO squared O2 concentration. So these are all Kc. Now if you have a pure solid, what do you do with a pure solid? Yeah, activity is 1. And so we aren't going to have a concentration for zinc. The concentration of zinc doesn't change. The same goes for pure liquids. Pure liquids. Did I do this? No? All right. Then we have the Kp, and so it's the same thing. These are all gases, so that's okay. But here we have two solids and a gas. So the solids activity are 1 is 1. Here, this is kind of interesting because here they form gaseous CO2 and gaseous H2O. So this must be at elevated temperature. That's Kp. Then you want to know about formation reactions. So they're asking for Kc for the formation from its gaseous elements. 1 mole of HF, 2 moles of NH3. 2 moles would technically be 2 times the formation reactions. Formation from the gaseous elements. And then we have Kp for a similar thing. And then here we have Kc to Kp conversion. Kp is equal to Kc times T quantity raised to the delta N of gas. So what's delta N of gas here? Can you look at it and see? Delta N of gas, we're going from 1 mole on the left to 2 moles on the right. So delta N of gas is +1. So 1 to 2 is +1. Here we're going from 3 to 2. So we're losing a mole, so it's -1. Here we're going from 4 to 5. Yeah, +1 here. And so none of these have Kp equal to Kc. If delta N of gas is 0, then Kp and Kc are the same thing. But all these we'd have to do conversion. And so we would solve for Kc in this case. And Kc would just be Kp divided by RT raised to the delta N of gas. So that's getting Kc from Kp. This is the opposite. We want Kp from Kc. So we just use that equation to figure out delta N of gas. What's this? Delta N of gas. +1. This one? +2. And this one? +2. Yeah, that's all correct. The only thing that could trip people up is if there's solids and liquids in here. And you can't count those, delta N of gas. All right, so number 9, the vapor pressure of water at 25 degrees C is 23.8 millimeters of mercury. And so let's write Kp for the vaporization of water with pressures in atmosphere. What is the value of Kc for the vaporization process? And so this one, let's just do this one since it's quick. So vapor pressure of water, from vapor pressure, this is chapter 12, I think. We went to H2O gas. And so we did lots with vapor pressure already. But here, if we're looking at this, this is Kp, since we're dealing with gases as liquids, so Kp is just equal to the partial pressure of the H2O gas. Now, this is equal to 23.8 millimeters of mercury. And so all they want is, they want it in atmospheres. So we just convert this into atmospheres. And so that's 1 atmosphere for 760 millimeters of mercury. And so how many atmospheres does it come out to? So let's go ahead and check that. .03.8 divided by 760. 0.0313. 0.0313 atmospheres, which is close to what it is in bar. But since we got 3 sig figs, I'm going to carry 1 extra, so 0.3131 atmospheres. I think in bars it's like 0.032 bar. Is that correct? From the test. Now, this is Kp, and so Kp is equal to Kc RT. This equation is easy to derive, but you don't have to derive it or memorize it. You just give it to you. And so that means Kc is equal to RT delta N of gas over Kp. Now R, which R do we use for this? You can tell which R you use based on the derivation or based on just dimensional analysis. You just figure out the units, I think. No, units don't work out. You know, why don't units work out with these K expressions? In fact, you notice the chemists are pretty strict about units, putting in units. But if I started putting in the units for these K expressions, it gets really weird fast. But why is that? Why don't we deal with the units as we should properly deal with units? Anybody recall? No? It's a constant, yes, but it's not because it's a constant. I mentioned it before briefly. These K expressions should properly, if we were to do them properly, should be activities. The activities of gases is close to the pressure. The activity of solutions is close to the concentration. And it turns out activities have no dimensions. They're dimensionless. And so, okay. But anyway, we should know what R we should use for this. What R do we need to use for this? How did we derive this equation? Does anybody recall how we derived it? It's from the ideal gas law, so we should use the, not the 8.314, we should use the 0.08. Now, I have it memorized for atmospheres, but for bar, I would have to convert it, which isn't a hard conversion as long as you know the conversion from atmospheres to bars, but here they want it in atmospheres, so this is good enough. We'll just do it in atmospheres here. And so this is 0.08206. And the units here would be liters atmosphere per mole Kelvin, but you know what? The units aren't going to cancel out, as you'd expect, times 298. So we'll just do it. What's delta N of gas here? Well, maybe the units will cancel out. We don't need the units for Kp. Kp is going to be in atmospheres. Let's see if the units work out. And so 0.08206 liters atmosphere per mole Kelvin times T, which is 298 Kelvin, divided by Kp, which is 0.0313 atmospheres. Actually, you know what? Kind of. Did I screw this up? Yeah, I did. I screwed this up. Do you see it? Good thing I checked because I was getting, you know why I screwed this up?
1 over KC.
Yeah. So Kc is equal to Kp divided by RT, delta N of gas. Because I was getting liters per mole, whereas concentration should be moles per liter. So the units actually saved me here in this case, but normally we don't deal with units in the K value because those are based on activity. But let's take a look at this. Because it depends on what delta N of the gas is, because, you know, the thing that could screw us up is if delta N of gas is 2, then we'll get molar squared. So what the heck is molar squared? But you would just leave it as dimensionless. But in this case, you know, delta N of gas is, what is delta N of gas here? Even though we don't write the units like this, we would know that, you know, the number would change depending on the unit. So here, this is the Kp value in terms of millimeters of mercury, it'd be 23.8. This would be the Kp value in terms of atmosphere. In terms of bar, the Kp value is 0.032 bar. You know? And so the value changes depending on what unit we're using, so we have to keep track of our thermodynamic data. Is our thermodynamic data under bar, or is it under atmosphere, or is it under millimeters of mercury? But anyway, let's continue with this one. We're under atmospheres here for this particular problem, so this is going to be 0.08206 liters times atmosphere per mole Kelvin times 298 Kelvin. In this case, like I said, it depends on delta N of gas. Our delta N of gas here is, again, what was our delta N of gas? 1. And so in this case, you know, the atmosphere is canceled, Kelvin cancels. This gives us liters per mole. We flip it, we get moles per liter. So we get molarity of the first. If our delta N of gas was 2, we'd get molarity squared. If it was 3, molarity cubed. But would we worry about it? No, we wouldn't worry about it. It's because of the way it cancels, you know. The products over the reactants are in the same kind of numerical ratio, that is 1 to 1 or whatever. In this case, it's not. All right, so what we do is just plug this in here, and then we get the concentration. That should be the ratio for the concentration and molarity. So let's do this one here. Oops, I didn't need to delete that. 0.03131. I usually carry an extra digit in the calculation. I usually carry an extra digit in the calculation to minimize round-off error, or more. So I shouldn't have cleared it out of my calculator. I would have carried more. 0.08206 divided by 298. 0.01280 for the molarity. In terms of molarity, what we'd have to do is we'd have to figure out, because this would just equal, in terms of Kc, this would be the molarity of H2O gas. The molarity of H2O liquid, you know, doesn't change. It's 55.5 molar. So since it doesn't change, its activity is 1. It's actually incorporated. Right. All right, so that would be number 9. Let's look at number 10 here. You know, I saw some people were working on, if Kc is equal to 5.12 times 10 to the minus 3 for the equilibrium established between liquid benzene and vapor, what is the vapor pressure expressed in millimeters? So again, this would just be the Kc to Kp conversion. Now, we would have to know if the pressure is under bar or under atmospheres here, and make a slight difference. If we do it under bar, then we just figure out what Kp is, and then convert it into, from bar into millimeters of mercury. Here, determine Kc for this reaction. Kc is just going to be the NOBr concentration divided by the square root of N2O2 character. Oh, from the following information. So they give us some data here. I think I did this one. Did I do this one? Number 12? Yeah, we did that one in class. This one, basically, these ones aren't too bad. Like all Hess's law problems, sometimes you get stuck. If you get stuck, you just go back, keep going through it. Eventually, you'll get the correct answer. You just persevere there. An important environmental physiological reaction is the formation of carbonic acid, H2CO3, from carbon dioxide and water. Write the equilibrium constant expression for this reaction in terms of activities. Convert the expression into an equilibrium constant expression containing concentrations and pressures. You could do that one here quick. So I might have told you, one of the things I did as a student was I tried to do all the homework problems, not just the ones the instructor assigned in class, but all of them. But the thing is, there's not enough time to do all of them unless you kind of have some help, and the help you have is the solutions guide. If the problem is taking too long, you look at it in the solutions guide. And this way, what I do is I just go through all the problems, and then I'd concentrate on the advanced or the more challenging problems, to spend some time on those. But, when you do this, then you get the basics down pretty fast. And so this one, H2O liquid plus CO2 gas, gives us carbonic acid, H2CO3. This equilibrium is heavily favored to the left because of the H2CO3 aqueous. And so KEQ, which is a thermodynamic equilibrium constant, is just the activity of carbonic acid, KQ, divided by the activity of H2O liquid, divided by the activity of CO2 gas. So that would be KEQ. But we know the activity of H2O liquid is just 1, so this is just equal to the activity of H2CO3, AQ divided by activity of CO2 gas. And then this should be about equal to the concentration of carbonic acid divided by the partial pressure of CO2 gas. So we have this heterogeneous type thing where we have both concentrations and pressures in this thing. And so that's our KEQ. Okay, so that's what they want, converted into an expression containing concentrations and pressures, which we just did. All right, rust is caused by the oxidation of iron by oxygen. Write the equilibrium constant expression in terms of activities, then in terms of concentrations and pressures. So 16, iron solid gets rusted, and so we need two. We need 3 halves and O2 gas to form Fe2O3. This is spontaneous. This is favored to the right. This one's obviously favored to the left. And so here, this KEQ is going to be less than 1. We expect more reactants. In fact, a lot less than 1. This one should be greater than 1. We expect more product than reactant. If we look at KEQ here, KEQ would be the activity of the iron, 2O3 solid, divided by the activity of the iron solid squared times the activity of the O2 gas to the 3 halves. Okay, in terms of concentrations and or pressures, this one's not going to have any concentration because the activity is going to approach concentration for aqueous solutions, but we have 2 solids here, so the activity of the solid is 1. So this is just going to be over the partial pressure of O2 to the 3 halves power. Give me something. did we do this problem, number 18? Figure out the K for this reaction? No? Yeah? Yes? We did it? Okay, let me just repeat myself. But 17, 18, 19, these are all very similar kind of problems where you determine it experimentally. How do you determine it experimentally? You have to measure at least one of the equilibrium concentrations, and you have to know the initial concentration. And we set up an ice table and figure it out. So that's equilibrium. Constant expression. Sometimes we do some, some calculations, like in 21. Let's take a look at that. In number 21, write the equilibrium constant. Well, they give us a K. If they give us a K, then we aren't trying to determine a K. And so in this section, it's a little bit mixed. The first set of problems is the experimental determination of equilibrium constant. Our K is unknown, so we're trying to figure out what the K is by experimentally measuring some concentrations and or pressures. However, in the same section, they have problems in which they already give us K, here and here. If we already have K, then we don't have to determine it experimentally. It's already determined for us. So this is a different type of problem. This type of problem is a stoichiometry style problem. Once we have the K, then we can figure out the other values. Now, the other values here would be this. This one does not require an ice table, and so this is why they don't put it down here. But what I do is just a standard procedure is just write an ice table. It doesn't take very long, and then you get an idea of the variation, because if you set up all the problems the same way with an ice table, then what you're going to see is you're going to just see multiple variations of how you work with an ice table or how you solve particular problems. And so your book is going to completely skip an ice table for this, because we don't need it. Actually, the quickest way is to skip it, but we'll set it up. Because this stuff you could do in your head too. Once you're, Now, did they tell us, is that a KC or KP? Well, or KEQ? Well, in this case, there's no KP. There's no gases here, and so you'd assume that this would be a KC, which would be the same thing as KEQ in this case. And so that K is KC and KEQ, well, same thing. And so what we'll do here is this. We see that K is equal to 9.1 times 10 to the third. Now the K is going to equal the equilibrium concentration, right, of the iron 3. Now water is a liquid, so that's a 1. And then we'll have the H plus concentration at equilibrium Q. Now, what we do in an ice table is this. Now, if a solid or liquid appears in the ice table, the concentration doesn't change. The amounts will change, but the concentration doesn't change. If the amounts change and the concentrations don't change, we assume that we have enough. We're definitely, obviously, if we have 0 iron 3 hydroxide, nothing's going to happen. So we're just going to assume we have enough. In fact, we're going to assume we have more than enough. So if we consume it, it's okay. It's not the limiting reagent. Everything's going to reach equilibrium. That's our assumption. And so for pure solids and pure liquids, even if they give you an amount, we're not going to include those into the ice table. A lot of people make the mistake of trying to include these here. Don't. And so we'll figure it out now based on the information that's given. Okay, they want us to compute the equilibrium concentration of iron 3 plus a pH 7. At pH 7, H plus is 1.0 times 10 to the minus 7. Now, is this H plus initial, or is this H plus at equilibrium? And so does that H plus go here as the initial, or does that H plus go down here as the equilibrium? And this is, this is kind of like the semantics type thing. You have to figure it out by the way they word it. And so, and compute the equilibrium concentration for iron 3 plus at pH 7. So what does that tell you? Is that H plus at equilibrium, or is that H plus initial? This must be at equilibrium because they want the iron 3 plus when the pH is 7. And so that means that, okay, now solids and liquids are omitted from the ice table here. But the H plus, what we know is the equilibrium concentration here is going to be 1.0 times 10 to the minus 7 molar. Okay, this is at equilibrium, that's pH 7. And so here we don't know what the iron 3 plus concentration is at equilibrium here. But we can figure it out because when we look at the K and we look at the ice, there's only one unknown here. And that unknown would be the iron 3 plus, so just plug that in, solve for this. And so it would just be 9.1. I'll just go ahead and do that since this is not. And what do we do about the units? We ignore the units. And so here it's going to be 1 times 10 to the minus 7. 1 times 10 to the minus 7 cubed times 9.1 times 10 to the third. I get 9.1 times 10 minus 18. And so the iron 3 plus concentration at equilibrium was 9.1 times 10 to the minus 18 molar. The units would be molar there. Even though we ignore the units in the K, we'll add it at the end because concentration has to be in some of the units, molarity, whatever. All right, so this one, we didn't have an X value. We could have had an X value. We could have had a whole bunch of stuff. We could assume, normally we'd assume that there's 0 iron 3 plus initially, and so plus X. Well, X, that's what we're solving for. This is X here. And then the initial, we could actually figure out what the initial H plus must have been. We could have figured out the initial H plus. This would be a more advanced problem. And this is not necessary for this particular problem. And so we'll just do this as an aside. As an aside, if I wanted to fill in the rest of the table, I would have said, well, nothing's happened. None of this is solved. And this would be plus X. And therefore, this is X molar here, which is the iron 3 plus at equilibrium. That must mean this. That must mean we lost how many X here? This would be minus 3x. And then the H plus would have been the H plus initial, which we don't know what the initial was, plus 3x. So that, actually, would that be right? No, sorry. This would just be H plus initial. H plus initial minus 3x gives us this. We know what X is, because X must be the iron 3 plus concentration, so we can go back and figure out what the initial H plus concentration is. That will be an aside. So these are the types of variations that you see when you're doing these ice tables. If you do a whole bunch of these, then and you set them up in always the same way, then there aren't an infinite number of possibilities. There's a finite number of possibilities of the type of problems you're going to encounter. Did we do number 23? No? Okay. All right. Let's go on to number 23 here. Now I'm talking about variations. This is kind of nice because there was only one unknown, which we call X, or the iron 3 plus AQ. We just solve for that here. Sometimes there are multiple unknowns. If we have multiple unknowns, we want multiple equations to help us solve for multiple unknowns. And so looking at number 23, we have this reaction. It's 2SO2 gas plus O2 gas yields 2SO3 gas. And so basically I just set up an ICE table, this, and then just fill it in. The equilibrium amount of O2 in a 0.185 liter flask is 0.00247. Okay, so if we look here, they give us a Kc value of 281 at 1,000 Kelvin. So what we do here is, this is their Kc value at 1,000 Kelvin is equal to 281. So we can first figure out, well, it's Kc, so it's going to be concentration. So this is going to be SO3 squared. SO2 squared and the O2. In this case, Kc and Keq are not equal, because Keq, these are all gases, so Keq would be partial pressures. So in this case, Keq equals Kp. Keq equals Kp, which is not equal to Kc. But that's okay. We don't need it right now. Now they're giving us the equilibrium amount. We can't use amounts like moles. We have to use molarity, unless the ratios are the same. And here we have 3 moles of gas, 2 moles of gas. If this was 3 moles of gas going to 3 moles of gas, then we could have used amounts or pressure. But in this case, we'll have to convert it into molarity, which is 0.00247 divided by 0.185 liters. And so what does that come out to here? So 0.00247 divided by 0.185 is 0.01335. And so it says the equilibrium molarity of O2 is 0.01335, assuming I calculated that correctly. That would be it. Okay, what is the ratio of SO2 to SO3 in this equilibrium mixture? And so they don't give us much information. We have too many unknowns here. So here they don't tell us what the initials were. So what we'll do is we'll put in the SO2 at equilibrium is going to be here. The SO3 at equilibrium is going to be here. And so you go, well, there's not enough information to solve this problem. Sometimes they don't want you to solve the problem to a specific number. Sometimes they want you to solve the problem to an equation. Or, other times they don't give you enough information to solve the problem, so you solve it to limits. You say the lower limit is this, assuming this, and the upper limit is this, assuming this other number. So you make assumptions. But in this case, they want the SO2 to SO3 ratio. So what we want is the SO2 divided by the SO3 ratio equals what? So here, I know what my O2 is at equilibrium. I plug that in here. And I almost have the ratio, it's just flipped. And so what I have to do here is this. I have to invert this. And then if I invert this, then I got to invert that. And so this is going to be 1 over Kc, or 1 over 281. Invert it. And then if I invert times the O2 concentration at equilibrium, then take the square root of that. And the O2 concentration at equilibrium we already have over there, so it's just going to be 1 over 281 times 0.01335 square root. And that would be it. And so in this case, they aren't asking for us to solve a specific number. They're asking us to to solve for an equation, which is fine. This is an equation. Now once we have an equation like this, we can plug in some numbers and see how the ratio changes. Or, for every one of this, how many of those would we have? That type of thing. All right, let's go on to number 24 here. Number 24, for the dissociation of iodine at about 1200 degrees C. So iodine's bonds aren't terribly strong. And so what happens is high temperature, you dissociate. In fact, all molecules will dissociate at high temperature. All molecules. Because if you think about it, in the sun, are there any molecules? You think water is stable in the sun, or the hydrogen molecule, H2? What do we have in the sun? Do we have atomic hydrogen or molecular hydrogen? Atomic hydrogen. At high temperatures, there's lots of kinetic energy. Molecules aren't stable. This is an entropy effect, because here the entropy is going to be favorable. Delta S is going up, therefore it's favored at high temperature. So eventually all molecules will dissociate at some temperature, which we call high temperature. But anyway, for this one, 1200 degrees C, we have 1.1 times 10 minus 2. It's still not terribly big. 1.1 times 10 minus 2 is kind of small. What volume should we use if we want 0.037 moles of iodine to be present for every 1.00 moles of iodine at equilibrium? At equilibrium, so, if we have an ice table here, they're telling us the equilibrium. And so what they want here is they want 0.037 moles of I. So 0.037 moles of I for every 1.00 moles. And so this is not the concentration. This is the amount. So here I write EAMT to indicate that this is not what I'm going to use. In fact, I need the volume, but do they give us the volume? Because I need to convert it into molarity. So I want to go from amount to molarity by just taking the moles and dividing by the volume. Right? Now, they don't give us the volume. In fact, they want us to solve for the volume. And then it turns out this is just another variation of trying to solve for our unknown here. This is going to be the iodine, atomic iodine squared at equilibrium divided by the I2. And so this is going to be 0.037 moles per V. Now this is going to be squared. The units actually work out in this particular case, but even if they don't, we just solve for V, where it comes out to. Solve for V. So just a slight variation. What the point of doing every single problem, or at least looking at every single problem, what you do is you can just look at it and look at the solutions guide. The point of doing that is so you can see all the variations. Once you see all the variations, then you log those into your mind, and eventually what you can do is you can do new variations, your own variations, step by step. In the Oswald process for oxidizing ammonia, a variety of products is possible. When we oxidize ammonia, it depends on the strength of the oxidizer we use. And so what happens is like this. You could oxidize it mildly, or you could oxidize it vigorously. It depends. This symbol, have you seen this symbol before? This symbol is a symbol for oxidation, or oxidizer. Could be mild. Do mild ammonia is electron rich or electron poor? What's ammonia? Electron rich or electron poor? Or neither, maybe it's. Oh, well, just tell me the oxidation states. What are the oxidation states here?
H is +1 and N is, or, I'm sorry, H is, I'm sorry.
That's okay. It's tricky because in books, you know, some people would call ammonia nitrogen trihydride, and nitrogen, or these are the class of hydrides. But when you think about hydrides would have a negative charge on the hydrogen. In this case, hydrogen would not have a negative charge. When I was looking, you know, I was searching a European chemical catalog for ammonia. I couldn't find ammonia because they don't call it ammonia. You know what they called it? Nitrogen trihydride. That's why I couldn't find it. Thinking, how can a chemical company not have ammonia? But they did. Nitrogen trihydride. This is a little bit, as far as when we think in terms of oxidation states, it's a little bit wrong. Somebody have it?
-3 + 3.
Yeah, -3 and plus, not +3. Oxidation state, don't ever mix up. Don't ever mix up total charge with oxidation state. Oxidation state's always for the individual element. The total charges have to balance, but you know, the oxidation state is not +3. The oxidation state is +1. If this were nitrogen trihydride, it would be 3+ and H+, but we know this can't be. This is wrong. Why? Give me one argument that's wrong. I'm sorry? No. In terms of physical sense, you know, nitrogen can have +3. Did you know that? Nitrogen can have +1, +2, +3, +4, +5. Nitrogen is what we call variable charge species. Depends. Like carbon, you know, carbon's in group 4, so what charge should it have? +4? Or -4? Or what is it? So somebody tell me why. This is more thinking back to like chapter 10.
So because the hydrogens wouldn't be able to bond, because there's no lone electron pairs?
Well, counting electrons is this is not accurate. This is the extreme. What we always do is the true value, this is going back to chapter 10, the true value lies somewhere between the two extremes. When we do this oxidation state, we're looking at the two extremes. We want to know what the range is. Because if you focus on just the average, you don't know what the extremes are either way, right? Or this. So what we do is we look at the extremes and then try to place it somewhere between the two extremes by counting electrons in two different ways. We count electrons, and this is really important. This is really important if you continue on in organic chemistry and like that to understand chemical reactivity of organic chemicals, but also in this class as well, but more so probably in that class. It wouldn't, you know, the reason is which one's more electronegative, nitrogen or hydrogen? Nitrogen's way more electronegative than, well, not way more, considerably more. Hydrogen's not bad, you know. Even though hydrogen's in group 1 over there, its electronegativity is actually right in the middle of the periodic table, 2.1. That's why in this periodic table, you know, hydrogen is placed in two positions. It's placed with the alkali metals, and it's placed with the halogens. Probably the Well, if we mildly oxidize it, we'll go to N2. So we go from -3 to 0. And then if we oxidize it further, we'll go from 0 to +1. In nitrous oxide, nitrogen is +1. If we oxidize it further, we'll go from nitrous to NO, which is +2. And then we can go to NO2, which is +4. We see this happen with elements like nitrogen, like carbon, etc. Like, you know, which one of these forms? Well, it depends on the condition. You know, it might stop here, it might stop here, or you might get a mix of products. In fact, there's one reaction. This is going to be an aside. This reaction happens in automobile engines. Nitrogen's in air. And we have oxygen. So basically, in automobile engines, we can burn the nitrogen. Have you ever heard of burning? Can you imagine burning nitrogen? How is nitrogen a good fuel? Well, air is like 80% nitrogen. Is nitrogen a good fuel? Does it burn easily? No. So this is under extreme conditions. In an automobile engines, did I talk about this already or not? I already talked about this? All right. Did I talk about ethanol? No. What we do is we get a mixture of these guys here, which we call NOx. These are the NOx because we don't know, you know, how vigorous the conditions were in particular. But you know what we typically do, you know, since we don't know which one forms, it's like when you burn ethanol. When you oxidize ethanol, did I talk about this? This is related to the quiz, and the afternoon class is asking me so many questions. I give them way too many hints because I was expecting you guys to be able to figure this out. But since I gave them so many hints, I'll give you some hints as well. And that is, under mild conditions, you know, ethanol, and I don't know where you guys got this. Did you guys get this from Google or did you get it from the appendix? Because ethanol can be oxidized to acetaldehyde.
I don't think it's in the appendix.
Where did you get it from?
I didn't get that at all.
Some people got this as a product, right?
Yep.
Where did you get this one from? Maybe it was the afternoon class.
We got it from Chem A.
Appendix?
I remember it from Chem A.
Chem A?
Yeah, Chem 1A, sorry.
Chem 1A? Ethanol going to acetaldehyde? Okay. This is under very mild oxidizing conditions here. And so what I tried to, if we further oxidize this, we could oxidize it all the way to this, CH3COOH. So some people got this. Where did you get this one from? I was thinking, you know, where I gave, did I already talk about the, did I talk about Joshua Tree and the wine? Mm-hmm. Okay, in Joshua Tree I bought that wine, and what happened was a little bit of air got through the corkscrew and started to oxidize the wine. There's a little bit of oxygen. Will you call that mild oxidation or vigorous oxidation? A little bit of air got through the corkscrew and oxidized my ethanol to vinegar. Mild oxidation or vigorous oxidation? Vigorous oxidation? In other words, a tiny bit of O2 got in and converted my wine to vinegar. Mild or vigorous? Mild. I mean, that's not even 1 atmosphere of O2. That's mild. And so this is under mild. Mild oxidation, mild oxidation. You know, can you burn vinegar? Does vinegar burn? You burn it in your body. I mean, if you consume oil and vinegar dressing, does the vinegar have 0 calories or does the vinegar contain calories?
Has calories.
It contains calories. You burn it in your body. When you burn it in your body, what does it burn to? Well, it undergoes, actually, I got this backwards, sorry. Acetaldehyde is more oxidized. Anyway, I got it right. You burn it in your body and it goes to, does it go to soot? When you exhale, do you exhale soot particles, black soot particles?
Does it go to glucose?
Well, this is for energy. The glucose will come from, eating sugars and that kind of stuff, carbohydrates. Ethanol, this ethanol has a lot of calories, and so they have, people, including myself, if I drink, although I don't anymore, but if I drink a lot of beers, you're gonna get what they call the beer belly, which I still hard to get rid of. Anyway, this is carbon solid. Do you exhale soot? No. Do you exhale carbon monoxide gas? Why not? Why don't we exhale soot and carbon monoxide? No, what do we exhale?
Carbon dioxide.
Carbon dioxide. Because now we've extracted all the energy that we can out of that. Can we go to carbon trioxide? Or carbon tetroxide? Or carbon pentoxide? No, we got to stop at carbon dioxide. There's no more energy we can get from this, and that's it. Now tell me, these are the oxidation processes that can happen. But tell me, what's a better oxidizer? O2, which you inhale, or dichromate? Which one is a more powerful oxidizer? O2 that you inhale, or dichromate that you don't want to eat?
Dichromate.
Dichromate. Dichromate, in fact, is a very, very, what does it mean to be a strong oxidizer? And so this was the point I was trying to make. The point I was trying to make is you need to do some memorization. Chemistry is not just looking things up. You have to have some factual knowledge memorized. And if you have the powerful oxidizer like dichromate, there's no way this is going to stop here at acetaldehyde. There's no way this is going to stop at acetic acid. This is going to go straight to carbon dioxide. And so if you don't go straight to carbon dioxide, well, some people did go straight to the carbon dioxide. There's just some balancing issues. So that's why nobody, did anybody get it? But anyway, you should know, dichromate. Dichromate's a very dangerous oxidizer. And it should take this easily to CO2. The reason is this a great reducer? If this were a great reducer, then we'd probably expect NO2, or a powerful enough oxidizer. So it depends on the additions. But nitrogen is a very poor reducer, And so these are the types of things you because you want to memorize some reference points, hopefully some extremes. For sure you should know the extremes, the extreme reducers and the extreme oxidizers. And then you can place other things in between. That's what we do. In chemistry, we want to figure out, what the extremes are and then do whatever. Well, depending on the conditions, of course, depending on the conditions. You got a powerful oxidizer like dichromate, I expect this to go all the way to NO2. If you got a mild oxidizer, then, when I say powerful, we make the assumption we're using 1 molar dichromate, right? Because that's what the table assumed. But however, if we use micromolar, like a micromolar dichromate solution, then I wouldn't call that extreme. I'd probably call it mild, because there's barely any in there. The concentration's so low. So that's why redox is pretty complicated because of this. But what we do is we try to make it simple by fixing the concentration and other stuff. One possibility is this. So it goes to nitric oxide, or NO. So this would be nitrous oxide, nitric oxide, nitrogen dioxide. For the decomposition of NO2 at 700 Kelvin, write a chemical equation for the oxidation of ammonia to NO2. Determine Kp for the equation. And so this, this is, if we go ammonia to NO2, then this is what type of problem? Well, it is a redox. The reactions are both redox, but what type of problem is this? Is this the type of problem you've seen before? We need to go from ammonia to NO2, but here we're going from ammonia to NO. But this reaction has NO2, so if we do this, if we reverse this second reaction and then add it to the first, we get it. And so this is just Hess's law. This should have been in the Hess's law section. I don't know why they put it here. This should be in this section, right? Well, it's a little bit more because what they want is, you see, if we reverse this, the NOs will cancel out. And then the O2s just add here. And so to write the chemical equation, so that's like Hess's law. Then what do we do with the Ks? Well, if we reverse this one, we invert this one, and then when we add these two equations, we multiply the Ks. And so determine the Kp. And so this is like the other one. And so it's out of place. 26. At 2000 Kelvin, Kc is equal to 0.154 for the reaction of 2-methane going to C2H2 plus 3 hydrogens. This is a redox reaction as well. If 1.00 liters equilibrium mixture at 2000 Kelvin contains 0.10 moles each, what is the mole fraction of C2H2 present? Do you guys remember mole fractions from chapter 6? You'll have to remember this. I asked you to review this because this was gas mixture. But be careful because, like for example, when I was taking thermo, the professor didn't review anything. I had to go back. I actually went back and bought a book. I actually went back and bought a second general chemistry book so I could review by myself. And so you have to review certain things like this. The mole fraction, Na over M total, is equal to the pressure fractions, Pa over P total, which is equal to the volume fraction, Va over V total. This is always true. This is, we can convert this into percentage. If we want to convert it into percentage, then we times it by 100%. It gives us the percent by mole volume pressure. This is all the same number. This is always true. When is this true? Uh-huh. No, not that. It's something else. Yes. Well, it's always ideal. We're always talking about ideal gases from now on. Because at 1 bar, gases behave close to ideal. It's only when we get to 100 bar, 1000 bar, or very low temperatures. We're at 298. Gases are going to behave ideal for the most part. So the thing, did I tell you about I was listening to this, the Guinness Book of World Record holder. He was talking about memory. The guy memorized like 20,000 digits of pi or something like that. Did you hear that? But it's not like he read it once. Did you know that? He didn't read it once and then it was there.
You know what he did? He didn't memorize it like within a week. I think, well, I don't know how long it took him. But what he did was he kept going over it and over it and over it. And then he said, did I already talk about this? Yes? All right, then. I don't want to repeat it, but what did he say?
We kept doing it every day.
Yeah, he had the certain intervals that he would go back through it. And the same thing. If you, and I know some of you are planning to go to whatever, professional school, or take this test, or the MCAT. I know because a lot of people their goal is to get into medical school. But if you've already forgotten all of your Chem 1A stuff, do you know how long it takes to relearn that? I'll tell you how long, because my friend forgot all the Chem 1A and the Chem 1B stuff. And not only that, he forgot everything. And it took him 5 years, because he was working at the same time. It took him 5 years before he got an acceptable score on the MCAT, like before he felt he remembered it. And so it's so easy to forget. And so this Chem 1B stuff, the thing you should do is just review your notes, especially for the final. It's so easy to forget by the time you hit the final. I know this is last whatever semester, or maybe you had it a while ago, so it's completely erased. But this is when at constant V. This is what we call Dalton's law. Do you know what law we call this? This is a law. This is at constant P. We call this Avogadro's law. And so I wanted you to go back and review Dalton's law and Avogadro's law from chapter 6. Those are important in this case. So, what is the mole fraction? Well, the mole fraction is moles of C2H2 over the total moles. And so at 26, it's just, sometimes they'll ask you for Chem 1A style. Chem 1A style stuff. So let's just take a look at actually, mole fraction we'll see later. And so this is just setting up the ice table. What I want to do is I want to hop ahead, since we don't have that much time left. I want to hop ahead a little bit and talk about this section here. Direction and extent of chemical change. All these problems, what we do is we calculate Q. Q is just whatever you're given, the given ratio. Now, does the given ratio match the equilibrium ratio? So what we do is we look at K here, and if Q is too small, that is, we don't have enough product, then we expect forward reaction. If Q is too big, we got too much product, we expect reverse reaction. If Q and K are the same, then we expect no reaction because it's already at the proper ratio. It's already at K. And so sometimes we calculate Q and try to figure it out. But I want to show you something else. And so this is calculating Q and then figuring out the ice table. I'm going to do number 40 later. This number 40 is a Le Chatelier shift, but we did it qualitatively. For number 40, we're going to do it quantitatively, the Le Chatelier shift. When we do it quantitatively, there are some tricks that help us do the particular problem. One of the tricks, let me just show you before we come back to 40. 40 is a tough problem. 40 probably should be in the advanced section. This Le Chatelier's principle qualitative or super easy? Most people don't have much trouble with that. Now, sometimes the math gets really tough for these, and so there's some tricks that we try to use to help simplify the math, make it a little easier to deal with. And so let's take a look at number 90. Number 90, the math is tough. This. The solution is prepared having these initial concentrations. The following reaction occurs among the ions at 25 degrees C. What will be the ion concentrations at equilibrium? So this is just a Chem 1B stoichiometry problem. We got Kc. We got the initial concentrations. We just set up the ice table. So we got 2 Fe3 plus Hg2 2 plus. So we got iron 3, mercury 1. This is going to go to 2 iron 2s and 2 mercury 2s. So it doesn't look all that different than the problem we had earlier. The Kc value is given. The Kc is 9.14 times 10 to the minus 6. This is going to equal the iron 2 plus at equilibrium squared times the mercury 2 plus at equilibrium squared divided by the iron 3 plus at equilibrium squared divided by the mercury 1 ion concentration. All right, so this is our Kc expression. We go over here, we set up the table here. And this is kind of nice because they just give us the concentrations here. Concentration of iron 3 plus is 0.5 thousand molar. The mercury 1 is going to be 0.5 thousand molar. The iron 2 is going to be 0.03 thousand molar. And the mercury 2 is 0.03 thousand molar. Now, I don't know. Maybe this ratio is already at equilibrium, maybe not. What do you think? When you look at this, when I look at this, I see, this is 10 to the minus 6, so it's like 1 to a million, And so it looks as if it looks as if maybe I have too much product there. But then on the numerator, it's to the 4th, and the denominator is to the 3rd. So what I do is here, I want to fill in the rest of the table. So should I go minus 2x, minus 2x? What do you think? If I go minus 2x, plus 2x, plus whatever, minus x, sorry, plus 2x, that's going to make more product. Do I want more product? And so I don't know which direction it goes. And so it could be plus or minus. Does it go to the right or does it go to the left? Because I don't know what the ratio is. But I can quickly find out because what I do is I do a Q calculation. If I do a Q calculation, maybe I'm already at equilibrium. If I'm already at equilibrium, I don't have to do anything. And so Q calculations just take the concentrations as given, 0.03 thousand. Then we're going to square that. But this is the same, so it's going to be 0.03 thousand to the 4th. And then this is going to be 0.5 thousand. Okay, it's going to be squared here and raised to the 1st here, so this will be cubed. Here. And so we can calculate the ratio that we have right now and see, is it too big, too small? What is it? And so 0.03 to the 4th. So just square it twice. Divided by 0.5 cubed. 6.48 times 10 to the minus 6. Now, when you look at that ratio, is it too big or too small?
Too small.
It's too small. It's too small, therefore, we're going to have this. This should be minus 2x minus x plus 2x plus 2x. And this is molar, so we'll just put in molar here. And so at equilibrium, I'm going to get 0.5 thousand minus 2x molar, 0.5 thousand minus x molar, 0.03 thousand plus 2x molar, 0.03 thousand plus 2x molar. And then all I have to do is figure out what my x is. I could figure out what my x is because this is the type of problem we saw earlier. Same type of problem. And so we'll just plug it in here because we have our Kc value. And so this is going to be 0.03000 plus 2x squared. Actually, this is the same, huh? So we'll just raise it to the 4th. 0.03000 plus 2x to the 4th. This is going to be 0.5000 minus 2x squared. And then 0.5000 minus x to the 1st. And then solve for x. Can I square root it twice? No, that's not going to work. Okay, so actually, let me fill in some blanks here. Q is less than K, therefore reaction goes to the right. If Q is equal to K, there would be no reaction. If Q is greater than K, it should go to the left because we've got too much product. Can you solve for x? How would you solve for x? Guess and check. Guess and check. But what I'm going to show you is a little trick to make things a little bit easier. I wouldn't do this because this is kind of tough. I would do something like this. And so one of the first techniques that you can do is you can try to reset equilibrium. If we try to reset the equilibrium, what that means is this. So, for example, this equilibrium should be product or reactant favored? Reactant favored. And so let's say I have 50 gallons of water in this tub. And if I have 50 gallons, then maybe we expect 45 gallons over here, maybe 5 gallons over here, something like that, right? But what happens if I push all the water? Let's say I push all 50 gallons back. And so what I'm going to do is I'm going to reset this. What I do by resetting is this. I'm going to push all the water back to the left. And so rather than having 45 and 5, I'm going to have 50 and 0. There'd be no water on this side. And then I'd let it equilibrate. If I let it equilibrate, obviously it's going to shift to the right. Will I reach the same equilibrium? Yeah. And so this is the whole idea about resetting. What I'm going to do is not water. I'm going to push all the atoms to the left. As long as I don't lose any, as long as I don't lose any water, you know, if I have a total of 50 gallons, it's going to end up at a 45-to-5 ratio. As long as I don't lose any atoms, what I'll do is I'll just push all the atoms to the left, and that's going to make my life easier. How? Let me show you. And so we're going to try resetting this one. And so for the reset, actually, let me do this. For the reset, I use this. I'm going to push all the atoms here. And so what I'm going to do is this. I'm going to eliminate this, and I'm going to go here. I'm going to go plus 2y plus y minus 2y minus 2y. And so if I have my reset initial, it's going to look like this. I want to push all the atoms, so I'm going to lose all these. So I'm going to end up with 0 molar here and 0 molar here. And then over here, do you know what I'm going to end up with? Well, 2y is 0.03 thousand. And so plus 2y is 0.03 thousand. So this is going to be giving me 0.5300 molar here. And then half of 2y is 0.01500. And so this will give me 0.05150 or 5150. Do you see that? And that's because I know my minus 2y is 0.03 thousand molar. And therefore plus y is half of it, so 0.03 thousand divided by 2. And so that's what I'm doing. I'm taking my original initial, 0.5 thousand, adding half of 3,000, 0.03 thousand, which would be 0.01500, and then just add it here. Does everybody see how I got these? All right, what does this do? Well, what this does is this. One of the strategies for resetting is to get more zeros as your initials. The more zeros you have as initial, the fewer binomials you have to deal with. And so in this case, which way is this going to go? Can it go to the left? It can't. It has to go to the right because we have no product. And so the only thing is to lose reactant and gain product. So we're going to have minus 2x, minus x, plus 2x, plus 2x. And so at equilibrium here, we're going to have 0.5300 minus 2x, 0.5150 minus x, 2x, and 2x. And so what this does is this. What this does is this is the original K, K based on the first ice table, which we're going to get rid of. The K based on the second ice table there, or reset conditions, is going to look quite a bit different because take a look at this. Rather than having two binomials squared on the top, we're just going to have 2x squared and 2x squared. So 2x squared times 2x squared gives us 2x to the 4th. Divided by 0.5300 minus 2x squared times 0.5150 minus x. All right, and so do you see this is going to be a lot faster to solve than this with the guess and check method, successive approximation. But we also have to figure out what our first guess is going to be. And so what we do is we could do this. We can use one more tip or one more trick. So this one's called reset. And so useful tools to have is reset. And 2, we're going to make an assumption here that the change is small assumption. Take a look at this ratio. This ratio tells you that this equilibrium should be heavily towards the reactant. And if this equilibrium is heavily towards the reactant, then what this tells us is that the change here won't be huge, If this was a large K, then this would be heavily towards the product. And we always reset to the side, to the favored side in the equilibrium. And how did we know that the reactant was the favored side? It's because the ratio, product to reactant, there is 10 to the minus 6. And so if we reset to the favored side, then the change should be small because the reactants are favored, so we don't expect to make that much product. And so one way of thinking about the change is small is like this. If you, let's say you have a scenario like this, where this is like a swimming pool here. And over here we have a few drops of water. Let's say maybe a gallon of water. And so over here we'll put a gallon. Over here we'll have, let's put in 30,000 gallons. And so if we reset this, then what are we doing? Well, we're going to have, we're going to push all this over here. And so that's going to add another gallon to this. And so we'll have 30,001 gallon. And then we'll let it equilibrate. When it equilibrates, then 1 gallon will go over here. And was that a very big change, or did the swimming pool lose much water? And so we've done these kind of assumptions before. Oops, I'm out of time, so let me stop there.